A coin was flipped 1,000 times. It landed on tails 450 times. Find the relative frequency of getting a tail. Well, relative frequency is the number of times a tail was flipped, or the number of times we landed on tails, divided by the number of times the coin was flipped. Or a shorter version of relative frequency is what we want divided by the total. So we want the relative frequency of getting a tail. So the number of times we landed on tails will go as our numerator. So we want the number of times we landed on tails. We want tails, so that goes as our numerator, which is 450, divided by the total number of times the coin was flipped, or the total number of trials. So that's going to be 1,000. So it's going to be 450 divided by 1,000, which will simplify to 9/20, or changing it to a decimal, 0.45, or changing to a percentage, 45%. So the relative frequency of getting a tail is 0.45. A decimal is what we would usually go with. If we wanted to know the relative frequency of landing on heads, or getting a head, well, it's going to be 55, because if we landed on tails 450 times out of 1,000, then we must have landed on heads 550 times out of 1,000. Alternatively, you could look at it as relative frequencies must always add up to 1. So 1 minus 0.45 will give us 0.55. So relative frequencies must always add up to 1. A spinner with 5 equal sectors was spun 20 times. The spinner landed on the green sector 5 times. What is the experimental probability that the spinner lands on a green sector? So the relative frequency is going to be the number of times the spinner landed on green, which is 5, divided by the number of times the spinner was spun, which is 20. Or our short version is what we want divided by the total. So we want the relative frequency that we landed on green. So the number of times we landed on green is what goes as our numerator, which is 5, divided by the total number of trials. The total number of trials was 20. The spinner was spun 20 times. And 5 divided by 20 is 0.25. So the relative frequency of landing on green is 0.25. An experiment is conducted to show how the number of trials improves the accuracy of the relative frequency. Mick rolls a die and notes the number of times a 1 is rolled. So the number of times he landed on a 1. He records his result every 6 throws of the die. Note 2 dp equals 2 decimal places. So after 6 throws, he landed on 1 0 times. So his relative frequency is going to be 0. After 12 throws, he'd landed on 1 once. So his relative frequency would be 1/12, which is 0.08. After 18 throws, he landed on 1 twice. So his relative frequency would be 2/18, which is 0.11. After 24 throws, he landed on 1 5 times. So his relative frequency would be 5/24, which is 0.21. After 30 throws, he landed on 1 5 times. So his relative frequency would be 5/30, which is 0.17. After 36 throws, he landed on 1 6 times. So his relative frequency would be 6/36, which is 0.17. After 42 throws, he landed on 1 8 times. Relative frequency 0.19. After 48 throws, he landed on 1 9 times. Relative frequency 0.19. After 54 throws, he landed on 1 9 times. Relative frequency 0.17. After 60 throws, he landed on 1 11 times. Relative frequency 0.18. So you should start to notice that as the number of throws increases, so the number of trials, the relative frequencies get closer together. So we can see that after 30 throws, they all seem to be around 0.17, 0.19, 0.18. So they seem to stay around the same number. So the greater the number of trials, the more accurate the relative frequency will be. Mick then plots his results on a graph. So along the x-axis we have the number of throws, and along the y-axis we have the relative frequency of getting a 1. So after 6 throws his relative frequency was 0. So we're at 6 on the number of throws axis, the y-axis, and we're at 0 on the relative frequency of a 1 axis. After 12 throws, his relative frequency is 0.08. So you go to 12 on the x-axis and 0.08 on the y-axis, which is about here, and plot our point. After 18 throws, his relative frequency is 0.11. So go to 18 on the x-axis, 0.11 on the y-axis, and plot our point. After 24 throws, the relative frequency is 0.21. Let's go to 24 on the x-axis and 0.21 on the y-axis, which is around there. After 30 throws, the relative frequency is 0.17. 30 on the x-axis, 0.17, which is around here on the y-axis. Plot our point, and so on. So the next one is plotted here, then this one, this one, this one, and then the final one at 60 throws. And then we join them together with a ruler. So he notices that the more the experiment is repeated, the closer the relative frequency is to the estimated probability. So the estimated probability of landing on a 1, if we roll a fair dice, the probability of landing on a 1 is 1 over 6, because there's one on a die, and there are 6 options in total, 1, 2, 3, 4, 5, and 6. And 1 over 6 changed to a decimal is 0.16 recurring, which we can round off to 0.17. So Mick notices that the more the experiment is repeated, the closer the relative frequency is to the estimated probability. In this 1 over 6, or 0.17, to 2 decimal places. So we notice this blue line drawn in, which is at 0.17, and we can see that the further along we move our graph, the closer our relative frequencies get to the blue line. And we would imagine that if we were to continue on our number of trials, so if we were to continue on our graph, moving our x-axis along as far as we can go, we would eventually, we predict, just have a straight line, because the more trials that you perform, the closer you'll get to the real probability, the closer the relative frequency will get to the actual probability.